Okay, let's dive into this. Right now, the entire electric vehicle industry is racing toward one massive ultimate goal. We're talking about giving you the ability to pull up to a charging station, plug in, and get 400 kilometers of range in just 10 minutes. I mean, it's literally the holy grail of EV adoption, right? Making charging just as fast and convenient as filling up a regular gas tank. It would completely wipe out range anxiety once and for all.
But here's the fascinating and kind of frustrating reality behind that super ambitious 10-minute charging target for 2026. With our current standard battery tech, it's physically impossible. You literally cannot push that much power into today's EV batteries that fast without risking a catastrophic failure. The whole industry has basically slammed into this hidden microscopic wall. So, what exactly is holding us back? And more importantly, how do we break through it?
Well, to answer that, we're going to walk through a few things in today's explainer. First, we'll look at the fast charging bottleneck, then the plastic separator problem. After that, we'll introduce an unexpected agricultural hero, take a trip inside the nanohighway, look at the green battery economy, and wrap up with a timeline to reality. So Section 1, the fast charging bottleneck. The big industry target for 2026 is hitting an energy density of over 400 watt-hours per kilogram, all while keeping that ultra-fast charging capability. But getting those two things to actually play nice together is turning into a huge engineering headache. Which brings me to a question you're probably asking. Why can't we just charge an EV in 10 minutes right now? Our charging stations are definitely getting powerful enough, right? Well, it's actually not about battery capacity or the chargers anymore. It all comes down to the inescapable physics of heat. When you try to force that much raw energy into a battery cell in just 10 minutes, it generates a frankly terrifying amount of thermal energy. So the crucial point is that right around 130 to 150 degrees Celsius, standard batteries hit a very dangerous thermal ceiling. Basically, at this limit, the internal components of the batteries start to break down. We're not talking about a little dip in performance here. We're talking about the physical melting of the battery's internal architecture, which completely shuts the whole charging process down. Which brings us to Section 2, the plastic separator problem. Because there is a very specific, microscopic culprit inside these high-tech batteries that is melting and causing all this trouble. Deep inside every single lithium-ion battery cell is a battery separator. It's essentially this ultra-thin plastic film, usually made out of fossil fuel-derived stuff like polyethylene or polypropylene. Now, its whole job is to physically divide the positive and negative sides to prevent a short circuit, while using tiny pores to let lithium ions pass back and forth. But here's the catch. These plastic films were originally designed way back in the 1990s. They were built for slow overnight charging in your garage. They absolutely were not made to handle the extreme 200 to 300 amp surges you need for a 10-minute fast charge. Think of it like a highway. During a slow overnight charge, the lithium ions just cruise through that plastic separator. It's smooth, steady traffic. But when you hit it with an ultra-fast charge, billions of ions try to rush through those tiny, uneven plastic pores all at the exact same time. It creates a literal microscopic traffic jam, the ions bottleneck, causing severe friction, which generates massive amounts of heat. That heat blasts the battery up to that 130-degree ceiling. The plastic actually begins to melt, the pores squeeze completely shut, and bam, the battery shuts down and your efficiency is ruined. Okay, let's move to Section 3. The unexpected agricultural hero. And I am so excited about this part, because the way we solve this high-tech EV problem actually involves a wildly unexpected, very low-tech plant. Because the big multi-billion-dollar question is, how do we replace that plastic? Well, researchers found the answer in carbonized industrial hemp. Yeah, you heard me right, an ancient agricultural crop. It turns out that hemp is basically the perfect biological solution to this chemical bottleneck. Over millions of years of evolution, the internal structure of the hemp plant evolved into this incredibly efficient, highly porous network that is just naturally designed to transport water and molecules perfectly. And engineers, they figured out how to hijack that exact biological architecture and put it inside a battery. So here's how they actually do it. They take raw industrial hemp fiber, which is cheap and everywhere, by the way, and they put it through a process called carbonization. They basically bake this raw fiber at extreme temperatures, like 800 to 1200 degrees Celsius, in a totally oxygen-free environment. That intense heat strips away all the organics, water, gases, the whole shebang. And what you're left with is the plant's original cellulose matrix, fully transformed into this highly conductive, practically indestructible carbon skeleton, a literal nanosheet.
Let's take a closer look in Section 4. inside the nanohighway. We're going to zoom right down to the microscopic level to see exactly why this baked agricultural waste is absolutely crushing advanced petrochemical plastics.
Now, what's really interesting about this structural comparison is exactly how they match up. Traditional plastic has these random, easily blocked pores, but the carbonized hemp, it keeps the plant's beautifully organized nanochannels. These pores are perfectly sized between 5 to 50 nanometers. And since a lithium ion is tiny, only about 0.76 nanometers, the hemp structure acts as a totally frictionless multi-lane highway, no traffic jams whatsoever. Plus, remember how plastic melts at 130 degrees? Well, carbonized hemp is thermally stable way past 1,000 degrees Celsius. It's just not going to melt during a 10-minute charge. And because this hemp nanosheet completely prevents those ion traffic jams, it also stops one of the absolute worst battery killers out there, lithium plating. See, in plastic separators, when ions get stuck in traffic, they clump together and form these microscopic metal needles called dendrites. And those needles will literally puncture the battery from the inside out, destroying it over time. But hemp's organized nanohighway lets the ions flow so smoothly and evenly that those destructive little needles just never even get the chance to form.
Which brings us to Section 5, the green battery economy. Let's zoom back out for a second, because this one microscopic fix has gigantic macro-level implications for the global supply chain.
By swapping out a tiny piece of plastic for carbonized plant matter, the economic and sustainability benefits are just staggering. Check out this incredible number, 2,000 plus. In rigorous testing, batteries using these hemp separators survived over 2,000 extreme fast charge cycles while losing less than 5% of their total capacity. That's insane. Standard plastic batteries lose a massive chunk of capacity under those same conditions. With hemp, an EV battery could easily last 10 to 12 years of ultra-fast charging without degrading noticeably.
And then you have to look at the environmental and cost contrast, which is just as stark. Producing fossil fuel polymer separators generates about 3.5 tons of CO2 per ton of material. The hemp separator drops that carbon footprint all the way down to just 0.65 tons. That is roughly an 8 times reduction in CO2. Plus, industrial hemp is dirt cheap. You're looking at maybe $2 to $3 a kilogram to produce, compared to the $3 to $5 you're currently spending on complex petrochemical plastics.
And this brilliantly illustrates the greatest advantage of all, drop-in compatibility. You've probably heard a lot of hype about experimental solid-state batteries, right? They also promise fast charging, but they require the industry to completely rebuild billions of dollars worth of manufacturing infrastructure. Hemp nanosheets, on the other hand, can be rolled directly into existing gigafactory assembly lines right now as a one-to-one replacement for plastic, with hardly any retooling. It enables smaller battery packs, drastically lowers internal resistance, and you're making it out of cheap agricultural waste. It is literally a manufacturer's dream.
All right, wrapping up with Section 6, the timeline to reality, because you're probably wondering when you can actually go out and buy a car with this tech, right? Let's manage those expectations and look at the actual roadmap.
Looking at the data, 2024 and 2025 have been totally dedicated to highly successful lab prototypes. By 2027 and 2028, we expect to see actual pilot batches operating in consumer vehicles on the road. And then by 2030 to 2032, we're looking at true global mass production. Now, I know 2030 sounds kind of far off, but automotive safety certifications for crash and stability testing just take years to complete. The momentum is definitely there, though. Industry heavyweights like CAT-TL and LG are actually running pilot projects with this exact technology right now. I want to finish up this explainer with a really profound thought straight from the research material. They note that the next generation of EVs will be truly green inside, not just lacking a tailpipe, but green all the way down to the molecular architecture of the battery itself. Just marvel at that for a second. The cure for modern range anxiety, the absolute key to the 10-minute charge, wasn't waiting to be discovered in some billion-dollar synthetic chemistry lab. It was quietly growing in a farm field all along. So I'll leave you with this. As we push toward a fully electrified future, are our greatest technological breakthroughs going to come from inventing new synthetic materials, or from finally learning how to harness the perfect engineering that nature has already provided?